So if you're like me, after you see this electron configuration notation, you're like, my goodness, this thing is huge. How is that going to help me? It looks way too complicated. Luckily, we got a shorthand, and that's what we're learning about this time. The shorthand is pretty brilliant because essentially what it says is on the periodic table, you end at any of the noble gases. In fact, that's where all of these want to get. It's the most stable state that you can be in. Because those are super stable, you usually don't add or lose any electrons past the noble gases. Due to that, we can sum up a whole lot of those big long notations with putting a noble gas and then just the sublevels past that that end up making it another element. All you're doing is you're listing the configuration after the noble gas of a previous period. So this is our previous example of our full notation for 10, element number 50 on our periodic table right here. And it has a whole lot of orbitals that it takes up. But if we look at the energy level before where we find 10, so we find 10 on energy level 5, right, or period number 5, the noble gas of 4 is krypton. Now, krypton, it already sums up a large portion of this. In fact, it sums up all the way to where that P4 is. So all of this is essentially just that Kr krypton, okay? Since we can sum all of that up in that, we can rewrite 10, and we can say that the shorthand for 10 is nothing more than Kr, and you usually put some sort of brackets to indicate that you're using it as a sub. And then we have to put whatever was after it. So we still have 5s that has 2 electrons in it. We have 4d that has 10 electrons in it. And we have 5p that only has 2 electrons in it. And this works for 10 as well. We can now use this as the shorthand for 10 because that noble gas, it's going to lock things down. And the reason it locks things down is because this is the most stable state you can possibly get in is when you get to the noble gases. And that's why this would work. So that leads us to this idea of what is the most stable. Noble gases are the most stable. They're the least likely to ever get rid of or take in an electron. So once it gets to that state, we say it's pretty much locked down there. To be a little bit more stable, but not nearly as much as a noble gas. Remember, this is by far how much it is on the noble gas. You just need full orbitals. So even a full s orbital or a full d orbital, full f orbital, and definitely a full p orbital, because that's where we get those noble gases, is going to have a good stability. Next would be half of the sublevel, so halfway through here in our Ds, in our Ps or Fs, and then everything else is just really, really unstable at all times anyway. And if you think about that halfway point, this should make sense because remember there's 3 orbitals here, so this means each one has an electron. Everyone has an electron, but only spinning in one direction. But still, the big thing for us to remember is the reason we can do this notation, the shorthand, is because the noble gases won't give up or let or take in any more electrons. So it's going to be stable up to that point, and then any other sublevels might be able to take or lose electrons for that element. All right, hope that helped.